So this is a quick screencast for the workshop for week 11 for GIS and Spatial Stats. So I'm Jonathan, if you haven't listened to my voice before. So we're going to go into the portfolio modelling exercise, and we're just going to work through the workshop. So the bit you need to hand in is the portfolio bit, but of course you need to work through the workshop first in order to know what you're doing. So I'm going to save it somewhere where I remember where it is, and then we can load it up in RStudio. Okay, so essentially we're going to be looking at kernel density estimates, adaptive kernel density estimates, a bit of relative risk, and then we'll be looking at some spatial modelling. So we're going to load in our packages, so tidyverse, spatstat and spar, which I think you should have installed already. Okay, and then we're going to have a look at our data. So the data we're looking at is a planar point pattern of class PPP containing 1036 points, and it's a multi-type point pattern, so it's a marked point pattern. So it has two different, so it has X and Y, and it has whether it's cancer of the larynx or cancer of the lung. Okay, so it's quite a famous data set from the Chorley and South Ribble area of Lancashire in the UK. And essentially, the key question is whether the cases, whether the larynx cancer cases are differ from the location of the lung cancer cases. So essentially, what we're looking at is primarily to do with the larynx cases, and we're going to be using the lung cases as, if you like, a comparator, a denominator data set, which may have some common cause, right? So it's cancer of the larynx and lung are both reasonably, well, cancer of the larynx is quite rare, but you might think that the risk factors for developing any cancer might be similar, so that's why we're using lung cancer as a sort of a baseline. So the coordinates here, the X and Y, are linear, so we don't have to worry about the CRS for any of this, other than if we wanted to put them onto a map with other stuff, right? So if we wanted to put them on a map of the UK or something, we would have to then align it to the map via ST transform or something like that. Okay, so we're going to start by exploring the data just using the plot tool. So if we just plot the Chorley dataset, we get this here. So you can see that we have cases of lots of cases of lung cancer around this irregular polygonal region, and then we've got some cases of larynx as well. And it's a little bit hard to see what's going on here because largely because the blue is often on top of the red. Okay, but one thing we can see is that both distributions are certainly the distribution of the lung cancer, the blue dots, are very much not random across this area, right? If they were random across this area, we'd expect to see some points down there. They're very, very highly clustered, right? So that means that a complete spatial randomness doesn't apply, and so we need to really describe this with some non-constant trend, right? So some inhomogeneous Poisson process, for example. Okay, so this next block just pulls out things so that we can see them a little bit easier just by building the same plot ourselves, right? So we're going to plot the window, so we're going to split out the larynx data and the lung cancer data, and then we're going to plot the window, which will give us the polygon, and then we're going to put the points on top of it. All right, so if we run the whole lot, we get that point there, and by plotting the larynx cases on top, we can see where they are. And as you would expect, the distribution of both sets of points are actually quite similar. Probably because this distribution that we're seeing is likely just the underlying distribution of the region. If you actually go onto Google Maps, for example, and if you look up the Chorley Ribble area in the UK, then you'll see that there's some townships, right? These big blobs here are basically a bunch of different townships. And that's what we're seeing, right? In order to have people with disease, we need to have people first. And that's what we're seeing here on this map. But nonetheless, perhaps there is some differences between the red and blue, and that's what we're going to be exploring today. So this is using base R graphics. You can use ggplot as well. The key thing to do is to convert everything to a data frame first. So if you're familiar with ggplot, then you can use those tools. I typically use ggplot because I like a little bit more control over the plots, and also sort of a little bit more consistency from plot to plot. And so that's the same thing with ggplot. The chord fixed here is to make sure that the x and y coordinates are on the same scale. Without the chord fixed, then they could be scaled separately, which of course you don't want. These are in kilometres, so we want them to we want a square scale kept, so the distances, etc., are representative. So what do you think of the distribution of larynx cases compared to lung cases? Do they roughly follow the same distribution? Yes, the larynx cases do seem to follow roughly the same as lung cases. Possibly as both are mostly driven by where people are. What might you do to confirm this, do you think? What could we do to confirm whether they might be the same or different? Well, I guess one thing we could do is we could do something like take the distance of each red point to each blue point and compare that to the distance of each blue point to each blue point, perhaps. That might be one idea. Perhaps an easier idea might be just to do a kernel density estimate of each one and see if they line up. Do they end up looking similar? Even better is perhaps do a relative risk estimate. So we could look at the ratio. So we could use compute a kernel density estimate for the red points, kernel density estimate for the blue points, and then we could look at the ratio of one over the other and see whether it's, what we'd expect is it to be constant, right? It should equal 1 if the two distributions are the same. Okay, so let's start having a look at the pattern. So we could use density from the SpatStat package. So there's the density of larynx cases. So notice that we can see this is quite strongly over-smoothed. While we don't have much data here, we expect to have a little bit more detail than just two big blobs. So we could have a look at what the smoothing amount is at the moment. So it's currently 2.7, and we could perhaps reduce it a bit. Okay, so here's the smoother with sigma equals 1, which gives us some more detail, and this of course is where these townships are, although I think this blob here might be something else. I don't think there's that many lung cancer cases down here. So that's the larynx cases, and we could do the same thing for the lung cancer data, right? So we could just copy and paste that in and do the lung cancer data. Whoops. Probably should spell lung correctly. Right, run that. Okay, and so we can see that there is a little bit of difference, isn't there? There's a little bit more weight up in here in the larynx cases, and a little bit down here as well. So does seem to be some areas where the density of larynx cases is higher than the density of lung cases. e.g. in the south. Okay. Now these are using fixed bandwidth estimation, so we've got a common bandwidth across the area. But you notice that there's a few sort of splots here and there that are likely due to not very many points. So we've got a little bit of undersmoothing in the areas where there's no people, and so an adaptive estimator might be better. And so we can do that with bivariate density from the SPA package. So let's run that. Takes a little while. So we do larynx data and lung cancer data, and then we plot them all. So here's the larynx cancer data. So you can see here that the blob over here is mostly gone now. And here's the lung cancer data. And you can see here that the blobs largely coincide, except for this one down here, right, which is missing on the lung cancer data, but it's present on the larynx cancer data. Okay. So we can also compare with our fixed estimates up here. So if we look at the lung cancer data, you can see that the it's not smoothing as much in the where the towns are, and it's smoothing more in the countryside. And the same with the larynx data. So if you look at this one and compare it to this one up here, you can see we've got this sort of undersmoothing out here, which is gone in this picture here. Okay, so the adaptive estimate seems to be better, particularly with the larynx data. Spaces, so regions where there aren't any observations are undersmoothed with the fixed bandwidth. And this is fixed in the, maybe we'll use remedied in the adaptive estimate. Okay, so now we need to compare these two things, and what we can do is we could use the ratio of them, okay, which is for risk. So we can use the risk function in SPA to do this, and this gives us now a ratio of the two. And so you can see here that for most of the region we have this yellow or orangey colours, which are basically log risk. So this scale here is a log scale. Log risk 0. So if the log of the risk is 0, then that means the risk must be 1, right? E to the 0, or anything to the power of 0 is 1. Okay, so for the vast majority of the region, the risk is 1. In some areas it's lower than 1. Right, so we have these areas here of very low risk of larynx compared to lung. Another blob over here with low risk. And potentially we've got spaces of high risk. It's hard to tell. Maybe down here, maybe over here, maybe up here. It's hard to tell mostly because this colour scale really sucks, right? It's not differentiating bigger than 0, which is risk, from less than 0, which is no risk. Okay, most of the values in the surface are actually in this range, and it's just that we've got this sort of big blob over here of nothing, no larynx cases because there's no people over there. That's sort of making the scale go all wonky. So so I've already answered this question here. Why do you think a log scale is used here? Well, I didn't answer it really, did I? But there's a good hint there. So the reason that we use a log scale for risk is that we want a double risk of larynx compared to lung to be represented by a similar magnitude as the double risk of lung compared to larynx, right? So if you swap the roles of lung and larynx, twice the risk should be the same in both cases, right? But if we use normal risk, the risk ratio, right, it's going to be, if we're doing larynx divided by lung, if larynx is twice as risky as lung, then that's going to be 2 divided by 1, which is 2. Whereas if lung is twice as has twice the density as larynx, it's going to be 1 divided by 2, which is a half, right? And the neutral risk is 1. The distance from 1 to 2 and from 1 to a half are different. But when they're put on a log scale, these magnitudes are the same. So on a log scale, these magnitudes are the same. i.e. log 2 is the same distance from log 1 as log half is. Okay. So we can improve the colouring here with a bit of work. Essentially what we want to do is we want to split up this colour scale. We want to specify the colour scale ourselves, and we can do this with this code down here. So let's have a look and see what this is doing. It's a little bit of work. So essentially what we do is we want to give a range of values for which we want colours. So if you have a look at colour breaks, okay, we've got -2 through to 2 separated by 0.1, right? So that's centered at 0. 0 is right in the middle. 0 being log 1, which is a relative risk of 1. And then we've got -10 and 10 at each end, just to make sure that we cover all the data, because our data went down to almost -10. So this just ensures it covers all the data. So the number of colours there is just the length of our break -1. So we've got 42 colours, and then we're asking for 42 colours that range from blue to red. Right, so if you have a look at cols, that's what the 42 colours are in hex, and then we're plotting the relative risk data with the breaks being here and our colours being there, like that. Okay, so let's run all that. Okay, so now you can see that the colour scale is centered at 0. So the neutral colour here, this grey colour, is at 0, so that's a neutral risk. The red is then a positive risk, okay, because the log risk is greater than 0, so risk is greater than 1, and the bluey colours are less risk. Okay, so that's so red colours, you've got more larynx cancer than compared to lung cancer, and blue colours you've got more lung cancer compared to larynx cancer. And so we do notice that there's a couple of blobs here that are potentially heightened, and maybe up here as well, which is a bit odd because we don't actually have any data up here. And the reason this happens is that we have there's few lung cancer points up here, so even fewer lung cancer points compared to the fact that there's no larynx cancer points, right? So this point here with a large amount of smoothing around it, because there's not many points in this area, is still adding a reasonable amount of weight up here to that density, more weight than than we're getting from the lung cancer plot. So do you think there's good evidence for any locations of increased risk given the number of observations you have in the larynx cancer set? So I think the best answer here is maybe. There are some areas of increased risk in the south and in the west, but we've only got a few cases there. 2 in the west and maybe 4 in the south. So so we should be a little cautious of claiming increased risk here without other knowledge being available to us. Okay, so the data alone is probably a little bit questionable here because we just don't have many larynx cases points. One way we can assess this is with the tolerance function in the SPA library. So essentially the tolerance function gives us a p-value surface. So for each location, you basically have what's the probability that the thing that we see here in our data, so the color or the intensity of the red there, what's the probability that we'd get that just due to chance, just due to random sample-to-sample variation, if in fact in the underlying population of people, the rates of lung and larynx cancer were the same. Okay, so the tolerance function can do this. Okay, and then we can plot it and add some contours. We get this here. And so we can see here that there does seem, or at least SPA seems to think that there is some evidence in these regions here that this is not just due to chance. Okay, so we do seem to have some statistical evidence for this. But I think we'd also still be a little bit cautious, particularly here. We've only got 2 points, right? So imagine the scenario where maybe that second person there hadn't gone to the doctor or hadn't got diagnosed with larynx cancer for whatever reason. Okay, perhaps it was missed. Then we wouldn't have that point, right? And if we just remove that 1 point, maybe having the other one there is now no longer important compared to the expectation we'd have given the distribution of lung cancer. So I think I'd still be a little bit nervous about this one. I'd also be nervous about this one, but maybe less so. They're very tightly clustered, and we've got 4. There's another one down here. There's 3 there, I think. And so I'm a little bit more certain about that one, but still not strongly certain. So let's write something up about that. So the tolerance, the p-value, tolerance contours are saying that there is some statistical evidence for these 2 regions, i.e. it's unlikely to be pure chance, where we should still be a little cautious, particularly in the spot where we have only 2 cases. Okay, now it turns out that there's actually an incinerator, an old incinerator, just here. Let's add it to the plot. So that's the location of an old incinerator. Okay, and cancer of the larynx is often associated, or is thought to be associated, with dioxins from the burning of organic solvents, which was something that was done in that incinerator there. And so we do actually have some external motivation for suspecting that there may be more cases of larynx cancer here, which suggests that maybe that's external to the data set. So the data set itself was telling us that maybe there's more cases of larynx cancer here than we might expect, given the distribution of lung cancer cases, which depends less on dioxins from burning organic solvents and more to do with things like smoking or other occupational issues. So I think there's more evidence here of the clusters of the point in the south. So the data itself was telling us to be suspicious of the cluster in the south. There did seem to be some evidence of increased risk there. That the incinerator is also there might give a plausible link or rationale for the increased larynx cancer rates. Definitely something to look into more. Okay. So for the last bit, we're going to look at modelling the larynx cancer rates using the lung cancer rates, the lung cancer density as a denominator for where people are, and then adding in the distance from the incinerator and seeing whether it's important statistically. So we're going to start by modelling just in terms of the lung density. So we've computed the lung density previously, right? So we could just plot lung.im. Right, so there's the lung density, and so we're going to model the distribution of larynx cases in terms of the log lung intensity. Right, so this is the model for the intensity of the larynx cases is on the log scale, which is why we use the log there. Okay, because we want the intensity of lung cases and the intensity of larynx cases to be on the same scale. Right, so that's the reason for the log. So let's run that for that model. And so what we see is that our log lung intensity here is important. More stars, more better. And in that increasing lung intensity, so increasing number of lung cases in a particular location, results in an increasing number of larynx cases. Okay, so as expected, there's a strong positive relationship between the location of larynx cases and the density of lung cancer cases. Okay, so why was log lung used in the model and not just lung? Okay, so I've already answered that. Is that the PPM model linear predictor is for log lambda, i.e. the log intensity. So we want our density or intensity surface for lung cancer to also be on the log scale. Okay, so now that we've modelled it in terms of where people are, we're going to add in the distance to the incinerator and see if that's important. So first we're going to have to do a bit of work in order to get the distance to the incinerator. So this is what this code starts with doing, right? So we let's have a look and figure out what this is doing. We're expanding, we're making a grid of all of the X coordinates from the lung cancer density and all of the Y coordinates from the lung cancer density. So if we have a look at points, let's have a look at what that looks like, right? So that's generating their X and Y, right? So we've got each X variable for every Y, all possible combinations of X and Y. So that's just all the pixels that we have, okay? And then we've computed, using that, we've taken the X and Y location from the points data set, and we've used the Chorley, the incinerator coordinates, and we've used cross-dist in order to find all of the pairwise distances from the location X, Y in our pixel data set to the incinerator. So this is just all of the distances. We've done the reciprocal squared of that. Okay, so that's what's in dist there. Okay, and then we are going to convert it back to a PPP object with the appropriate window in order to basically get the get things back as we want it, so that it's all because a lot of these points are going to be outside our region, right? This is just a square grid, and so we just want to crop those down using our window, and this is the one of many methods to do that. So here we go here. So that's our surface, right? So if we're very close to the incinerator, then the log of this distance measure that we've computed is high, right? So we're at risk of getting being affected by the incinerator, and as we move away from the incinerator, it falls away. Okay, and so now we can use that surface as a predictor in our as another covariate in our predictor for larynx cancer. And what do we see? Well, we see that the distribution of lung cancer is still important, right? So that's essentially a proxy for where people are. But then we see that the distance from the incinerator is positive. So the further you are away from the so the closer you are to the incinerator, right? So as you move towards the incinerator, right, the incinerator variable gets big, positive. So as the incinerator variable gets positive, so you're moving towards the incinerator, the risk of larynx cancer increases because we've got a positive estimate. However, it's not important. So statistically, that effect is not that important. It could be negative, such that the rates of larynx cancer actually decrease slightly as you move towards the incinerator, or it could be positive. Notice that it is sort of tending to one side, so we do have some evidence, but it's just not very strong. Okay, so our conclusion from this will be there's no, we don't have statistical evidence, a significant p-value for the effect of the incinerator after adjusting for the effect of lung cancer for the intensity. And part of that, I guess, might be because we do have a cluster of cases over here, don't we? Okay, if we look back at our risk map, we do have a cluster of cases over here that are actually quite far away from the incinerator. And of course, the incinerator might explain these ones, but it doesn't really explain these ones over here at all. And so that may be why we're not getting such a clear result in this modelling. So the last one is finally based on all we've seen. Do you think there might be a link between the incinerator and cluster of larynx cases in the south? And I would say overall, probably yes. It seems plausible that the incinerator could be responsible, at least in part, for the cases in the south, as we do have a closely, a tightly set of cases right near the incinerator. However, it's still only 3 to 4 cases, so we may not have strong statistical evidence for this. Certainly enough evidence to look a little closer. There we go. And so at the end, I'll just knit that just to make sure it all works. And so you can see that essentially in exploring this data set, the things that we've taken into account are, because we're modelling disease data, what is the denominator? Because we're modelling disease data, we think about using an adaptive density estimate, because we know that particularly for people are not homogeneously scattered across a region, right? People reside in villages and towns and cities. So we should expect spatial clustering, some underlying spatial trend as to where people are. And so we need to take that into account when we look at the distribution of a subset of people. Whatever it is, whether it's a disease or anything, we need to take into account where people live. I mean, this is a classic thing, right? You see, electoral maps, like, you have an election in the US, for example, right? And you see a map of the US and it's coloured red where the Republicans win and blue where the Democrats win, and all you see is the big sea of red. And that's because in the places where the Republicans win, there's hardly any people, right? It's this massive area, but there's not many people there. Okay, and even though the Democrats might actually win the election, more people may vote for the Democrats. More people have voted for the Democrats in the last 15 years, I think. the actual locations where they're doing so are in all the cities, right? So the cities tend to vote blue, Democrat in the US, and the more rural areas tend to vote red. And because there's more rural areas, when you just look at a map, it's just sort of telling you where people are. So the blue bits are where people are, and the red bits are where people aren't. So it's not actually useful for saying, where people are voting one way or another. All it's doing is basically showing you where people are. And the same thing happens in New Zealand as well. If you look at the last election, for example, where Labour won extremely convincingly, again, if you just look at the proportion of the vote across, Labour versus left versus right across the country, the areas where the right tends to do better are all the rural areas, which are generally larger. So the map is distorting your the view of the true underlying distribution, because we're not accounting for where people are. Okay. One way to get around that is to distort a map. So for example, let me see if I can find it. So here's my Twitter feed, this one here. So in order to get around this distortion, what you can do is basically replace the actual true space with a representation that is actually equi-weighted for size, if you like. So this is not equi-weighted for population, obviously. So in the Auckland area, there's many more people than there are, for example, in the Taranaki or the southern DHB. But nonetheless, it's somewhat getting around the problem of non-equal density. This is all proportions here too. So we're controlling for the baseline population. This is done using hex bins, so DH bins by Thomas Lumley at Auckland University. It's sort of I've sort of hacked it up a little bit to be able to produce it with ggplot, but that's sort of one idea we can use to deal with essentially the inhomogeneous nature of human populations across space. Okay.